Hello everyone. As a part of Midas training series, we will be discussing about boundary nonlinear time history analysis today. After this presentation, you will be able to appreciate the use of base isolators and dampers for the seismic design. Along with that, we will also be discussing about the various analysis methods that are used for analysis of such systems in softwares. The contents of the presentation are mentioned on this slide. We will start our discussion with the topic of basic idea of base isolation system. We will understand what is base isolation and what is the fundamental behind it. Then we will see the response of a base isolated system. We will compare the response of a structure with and without base isolation. Then we will discuss about the various base isolation devices that are available. We will be discussing about lead rubber base isolator and friction pendulum isolator. The next topic will be about the dampers, that how using the dampers we can limit the seismic response of a structure. After this section, we will discuss about some of the analysis techniques that are used in 3D FEM softwares for the analysis of base isolated systems. We will discuss about the comparison of Ritz vector and eigenvector, and for the analysis using the Ritz vector, we will see that how we can set up the analysis model. And I will be concluding the discussion with the comparison of model superposition and direct integration. So let us start our discussion with checking out the basic idea of a base isolated system. The idea of using a base isolator is that the force due to the earthquake should not be transferred to the superstructure. In order to do that, we should somehow isolate the base of the building from the superstructure. First idea in terms of layman language can be that we can lift the building using the balloons at the time of the earthquake. If we do that, then during the earthquake, the force of the ground will not be transferred to the superstructure, as the boundary between the superstructure and ground will not be there. The other idea can be using the magnetic leviation. In the magnetic leviation, we have to reduce the force transfer between the base and the superstructure using the magnets which get activated during the earthquake. This is the concept of base isolation in a layman's language. Now let us see how we can incorporate these two concepts in practical approach. How we can actually simulate the base isolated structure. One very important aspect of base isolation is that we should be able to restore the structure to its original position after the earthquake. If we do not restore the structure to its original position after the earthquake, then the idea of base isolation will not be practical. For the structure to come back to its restoring position, we have to simulate a restoring force during the movement of the structure. Now, this restoring force can be created in two ways. It can be done in the form of a rubber bearing, like mentioned in the first figure. So, like mentioned here, if we have a rubber bearing, then due to the deformation of the rubber bearing, a restoring force will be created and the structure will come back to its original position after the earthquake as a result of that restoring force. Now, the second idea or the second way of generating a restoring force is using the curved plate. This system is known as the pendulum isolator. The name pendulum is coming from the fact that using the pendulum isolator, the structure will move to and fro the center point, which is the basic definition of a pendulum. Using the rubber bearing, the elasticity of rubber will generate the restoring force. Now let us see the restoring forces in more detail. In this slide, we can see the set of restoring forces that will be generated in these two systems. As I mentioned that using the springs, the elasticity of the spring will be generating the restoring force. The time period of such a system can be calculated using this equation, where m is the mass and k is the stiffness. So here we have the gravity force acting downwards, and this is the inertia force being generated due to the earthquake. And the yellow arrows represent the restoring force that will be generated due to the presence of the springs. And then similarly, in the curved plate or in the friction pendulum, the time period of such a motion can be calculated using 2 pi root L by G. Here, this is the downward force and this is the inertia force. And the restoring force can be represented using the yellow arrows, which will be the normal to the point of contact. Therefore, if we summarize the prerequisites of a good base isolator, then we will have the following things in it. Capability of isolating the structure from the building, capability of isolating the ground from the structure so that seismic force is not transferred to the superstructure. The base isolation device should be strong enough to take the vertical load of the structure. Damping should be enough to have a significant base isolation result, and it should be capable of restoring the structure to its original position after the earthquake. Overall, due to base isolation, a lot of cost can be saved. The force experienced by the member in the structure is reduced drastically, hence saving the cost of the concrete and the rebar material. The vertical load is also reduced, hence saving the cost of the foundations. In this way, using the base isolation devices, we can have an economical design for the seismic structures. Now let us understand the base isolated system from the point of view of analysis. How does a base isolated system behaves for the analysis? If we try to simplify the structure, then it will be something like shown above. Base isolator can be represented as a spring, and the superstructure can be represented as rigid mass. So here we have a superstructure which we are representing using the rigid mass. And the base isolation level, the system can be represented using a spring. From the point of view of structural dynamics, what kind of difference can a base isolator bring in the response of a structure? This second figure will explain the difference in response of a structure with and without base isolation. In the conventional structure, we can see that deformation due to the earthquake and the deformations are quite high. But in contrary, in the base isolated structure, we can see that deformations are relatively low. Now let us understand this behavior a little more. So here in this graph, there is a comparison of acceleration of a structure with and without base isolation. So you can easily point out the difference. You can easily see that the acceleration of a structure with base isolation is much more less than the structure without base isolation. Now let us see the difference from a short video. So here we have a structure in which we haven't used any base isolator. With the lateral force due to the earthquake, the deformations in the structure are quite high, and hence we are getting cracks in the structures, and even there are a lot of deformations. On the contrary, a structure with a base isolator is not experiencing large deformations. So we can easily compare the behavior of a structure with and without base isolator here. Now in this section, we will have a closer look at the base isolation devices. We will try to explore the reason behind the unique capability of base isolation. As mentioned earlier, there are two types of base isolation devices normally used. First is the spring-based, that is the lead rubber bearing isolator. And the second one are the pendulum-based, for example, friction pendulum isolator. Let us start our discussion with the lead rubber bearings first. Lead rubber base isolator consists of rubber layers with steel laminated layers in between. So here we can see that for lead rubber bearing isolators, we have the layers of rubber with the steel lamination in between the layers. Also, there is a lead core, and hence the name lead rubber bearing is justified. Now, after going through the structure of a lead rubber bearing isolator, some of you might be thinking that why do we need to provide a lead core? The answer for this question can be easily understood by going through this slide. If the structure is without the lead core, then we can see that the loss of energy in the hysteresis loop is very less. So here, this is the isolator without the lead core, and as you can see, the loss of energy in the hysteresis loop is very less. Since the area of the hysteresis system represents the loss of the energy, so we can easily compare the loss of the energy with and without the lead core. After providing the lead core, the area of the hysteresis loop is increasing drastically, and therefore we need to provide a lead core. Lead core increases the damping of the system, and hence the loss of the energy also increases accordingly. In the lead rubber bearing, we have an axial spring, we have a shear spring, we can have a rotational spring as well. The stiffness of the spring can be calculated from this formula. If you try to explore about the input that we need to provide about the lead rubber bearing in Midas gen, then you will see that we have to provide the hysteresis loop parameter. So this hysteresis loop parameter A and B, we can easily compare the shape of the hysteresis loop for different values of A and B from these four figures. So here in this figure, the value A or alpha is 0.9 and beta is 0.1, and the loss of energy is quite high. And similarly, the graphs are being presented for various other values of alpha and beta. With the increasing alpha value, the curve gets thinner. With the increasing alpha value, the curve gets thicker, and energy dissipation gets more and more. The second type of bearing, as discussed, is the friction pendulum isolator. Due to a displacement U in the bearing, the restoring force generated in the bearing can be calculated using the formula shown here. Now here, this friction pendulum system consists of a concave surface. The concave surface can be upwards or downwards. In both the cases, the behavior of the bearing will be similar. The radius of this concave surface will affect the restoring force generated due to a certain displacement. For the purpose of analysis, this system can be represented using three types of spring: axial, shear, and bending. As discussed earlier, larger the area of hysteresis curve, more will be the energy dissipation in one cycle of oscillation. And if we try to visualize the working of a friction pendulum isolator, then we can understand the working of a friction pendulum isolator using this video. So here we can see that how the friction pendulum isolator is actually working. So this structure will be moving about this point and it will be creating a pendulum motion. For the input data in Midas Gen, we need to input various parameters about the system. For example, as I mentioned, the radius of the surface affects the force. So we need to specify the radius of the concave surface and we need to specify the friction coefficient. Similarly, we need to input the hysteresis loop parameter as discussed in the lead rubber bearing system. The definition of hysteric loop parameter is same. And we can even input the axial and the rotational springs as well. Now let us see some parametric effect for the friction pendulum, that how the radius of the concave surface and how the coefficient of friction will affect the behavior of the system. First thing that we should understand about the radius is that as the radius of the surface increases, the base shear that is generated at the base will decrease. If we keep on increasing the radius, and when it tends to infinity, it will become a perfectly roller surface. So if the radius of the concave surface is infinity, it will become completely horizontal and our support will be a roller support. Increase in the curvature will lead to increase in the stiffness and the displacement will also be reduced. Similarly, let us see about the effect of coefficient of friction. Now, friction pendulum needs certain threshold energy to be activated. The seismic force should be greater than the frictional resistance in order to generate any kind of displacement in the pendulum. If the seismic force cannot overcome the threshold friction, then it will become a fixed support. Along with that, increase in friction coefficient will lead to decrease in the displacement. Now let us compare the behavior of two systems. We will compare the lead rubber bearing isolator with friction pendulum isolator. In the first system, we have friction pendulum, and in the second system, we have the lead bearing. And we subjected both the structures to the same earthquake, and we can easily note the difference in the response of the two structures. Now, after the base isolators, The another kind of energy dissipation devices that are available for the structures are known as dampers. Dampers dissipate the seismic energy which is present in the structures. A typical visco-elastic damper consists of a fluid with a piston. The force of the fluid on the piston helps in dissipating a huge amount of energy during the earthquake. There are two types of dampers available in Midas Gen and Midas Civil. First is the viscoelastic damper and second is the hysteric system damper. They can be applied in various configurations in the building. So here we can see that what are the various configurations available and they can be applied in various configurations in the building. So we can have viscous damper, friction damper and yielding dampers. They all will help in dissipating the energy due to the earthquake. The response of a structure with and without damper can be easily compared from this video. Here we can see that displacement in the system with dampers are significantly less than the structure without dampers. In this way, we can save the structure during the earthquake using the dampers. So here you can compare the amount of displacements in the structure with and without dampers. There are three types of viscoelastic dampers available. First is the Maxwell model. Maxwell model consists of a linear spring and a viscosity damper connected in series. So here we have a linear spring and we have a viscosity damper which are connected in series. And then the second model we have is the Kelvin model. Kelvin model consists of a linear spring and a viscosity damper connected in parallel. And this is used for solid viscoelastic device analysis. Then the third type we have is more complex and it is known as damper brace assembly model. This actually consists of a Kelvin model damper which is connected to a spring further. So it is a complex system. In this section of presentation, we will compare the various analysis method of such a system. After going through this section of presentation, we will be able to make an assertive decision that while analyzing such systems, should we select the Ritz vector or should we select the eigenvector method for analysis? For boundary analysis, for boundary nonlinear times tree analysis, should we select the direct integration or the model superposition method for analysis? A comparison will be made for all such methods and the difference in results and accuracy will be presented. For the purpose of comparison, we will use a bridge model. And the bridge is using the dampers in order to reduce the seismic force. So this screenshot is taken from Midas Civil, where we are actually using the dampers for the structure. The dampers are presented in an actual structure like this. And if we try to have a closer look, the damper is like this. Let us compare the various methods now. So with all the permutations, we have three methods of analysis. The first method is nonlinear direct integration. The second method for analysis is modal superposition using the Ritz vector method. So we'll see that what are the various input data required for this particular type of analysis. And the third method that we have is modal superposition using the eigenvector method. In the first method, in nonlinear direct integration, we analyze each and every mode separately. and hence it takes the longest time to analyze. And we will be comparing rest of the two methods with taking nonlinear direct integration as the base. Now, if you compare the input of nonlinear Ritz vector, then you will see that in the Ritz vector, we have included 90 modes, but in modal superposition using the eigenvectors, we have actually included 270 modes. Clearly, for Ritz vector, the number of Ritz vector is 90. It is almost one third that we are going to use for the eigenvectors. Definitely, the time required for Ritz vector will be much less than the time required for the eigenvector analysis. Let us compare the results due to these three methods. So here we can see the bending moment. The first method is the nonlinear direct integration, and we can see that the maximum bending moment is the maximum positive bending moment is 4,434 kilonewton, and the bending moment that we obtained with nonlinear modal superposition for the Ritz vector is 4,428. So they are very close to each other, and the ratio for these two methods is 99.9%. So we can say that they both are yielding the same result. And in the third method, which is nonlinear modal superposition using the eigenvector, the accuracy is up to 99.6%, still quite close, and we can say that the results are quite same. For modal superposition using the Ritz vector, we can see that the results are accurate for all the forces, and for modal superposition using eigenvector, the maximum discrepancy is 112%. So using the method 2, we are getting almost the exact results, and we have used only the 90 modes, and the analysis time is also very less. In the above example, we have used 270 eigenvectors for analysis. The reason we have used 270 modes is that 270 is the maximum number of modes. So in order to have accurate results, we should include all the available modes, and hence we chose to input 270 modes. But for Ritz vector, we can see that there were only 90 vectors that were required to obtain an accurate results. Undoubtedly, as I mentioned, using the small number of vectors will require less time for analysis. Now let us see how are we getting this number 90. In this model, we have selected three starting load vectors. So we have provided three starting load vectors, and we have six general links, each with two nonlinear components. So we have 12 load vectors from there. So in total, we have 3 plus 12. In total, we have 15 starting load vectors. Therefore, the total number of Ritz vector will be 15 multiplied by 6, that is 90. So here we can see that using eigenvector, we need to specify 270 modes. Using eigenvector, no doubtedly we will obtain exact period and the mode shape. and we will get accurate results. But on contrary, with the Ritz vector, our periods and the mode shapes will be approximate, but the final result, that is the displacement and forces, they will be very accurate. So using the Ritz vector, we will get approximate time period and mode shapes, but our final result that we are interested in is displacement and forces. They will be almost exact using the Ritz vector. And in the Ritz vector, since we are using only 90 vectors, so the analysis time will be very less. We will also compare the analysis time in the next slide. So this slide mentions that how do we need to specify the starting load vectors for the Ritz vector. So we need to specify the starting load vectors in separate directions. Now comparing the above two methods from the perspective of speed and accuracy, we will obtain the results presented on the slide above. Both methods will give accurate results as long as the input data is appropriate. The advantage of using modal superposition is that it is very fast and the analysis time as compared to the direct integration method is very less. Here, if we try to compare the ratio of direct integration and modal superposition, then we can see that modal superposition is 34 times faster than the direct integration. And the accuracy, as I mentioned, the results will be accurate as long as the input data is appropriate. With this slide, I will conclude my presentation. Summarizing the takeaways, I would mention that the base isolators are effective in reducing the design seismic force and hence saving the cost of material. We have seen the various types of isolators and dampers available. For the analysis of such system in 3D FEM software, nonlinear model superposition method is recommended over direct integration method. Thank you.